Hey math enthusiasts! Today we're tackling a super interesting equation with towers of exponents. Check this out. X raised to the power of x raised to the power of x equals 16. And we're only looking at positive values of x. Looks pretty wild, right? Let's see if we can crack this mathematical puzzle. So I've got a hunch that x equals 2 might work here. Let's test it. If we plug in 2, we get 2 raised to the power of 2 raised to 2, which is 2 raised to 4, which equals 16 factorial. Wow, so we found one solution already. But wait, the natural question now is, are there any other solutions lurking around? Could there be some other value of x that makes this equation work? Let's, get a bit more systematic about this. To find all possible solutions, I'll define a function f(x) equals x raised to the power of x raised to x minus 16. This way, any value of x that makes our original equation true will make this function equal to 0. Pretty neat trick, huh? Now let's visualize this function on a graph. As we plot f(x), watch what happens. See how the curve crosses the x-axis exactly once? That's at x equals 2. And notice how the function keeps growing as x increases. It shoots up, super fast because of those stacked exponents. This confirms that x equals 2 is our one and only solution to this equation. How cool is that? Now we need to prove it. Let's look at an important property first. If a function is monotonic, either monotonically increasing or decreasing on an interval, the equation f(x) equals k, where k is a constant, will have at most one solution on that interval due to the one-to-one injective property of monotonic functions. Let's now prove that the function is moving in only one direction. We see that f prime of x equals the derivative of x raised to the power of x raised to the power of x. Our task is to calculate this derivative. Let's set g of x equal to x raised to the power of x raised to the power of x. Taking the natural logarithm of both sides, we get simplifying using the logarithm property, where the natural log of a raised to the power b equals b times the natural log of a. Differentiating both sides of the equation, we get g prime of x over g of x equals the derivative of x to the x times the natural log of x plus x to the x times 1 over x. Multiplying both sides by g of x, we obtain g prime of x equals g of x times the expression in brackets. And we can substitute back our original definition where g of x equals x raised to the power of x raised to the power of x, giving us this expression. Our next task is to calculate the derivative of x raised to the power of x. Let's define a new function, h of x equal to x raised to the power of x. Similarly, taking the natural logarithm of both sides, we have, continuing with the logarithm property, we simplify this to x times the natural log of x, differentiating both sides. We get h prime of x over h of x equals the natural log of x plus 1. Multiplying both sides by h of x, we obtain h prime of x equals h of x times the quantity natural log of x plus 1. Substituting h of x equals x to the power of x back into our equation. Finally, we have the derivative of x to the power of x, which is x to the power of x times the quantity natural log of x plus 1. Substituting the derivative of x to the power of x into our formula for g prime of x, we have this expression. Taking x to the power of x as a common factor and bringing it outside, we simplify the expression to this form, expanding the terms inside the brackets and simplifying, we arrive at the final form of the derivative. Therefore, we have calculated that f prime of x is equal to the derivative of x to the power of x to the power of x, which simplifies to this elegant result. For x greater than or equal to 1, we can see that all factors in the derivative are greater than or equal to 0, which means f prime of x is strictly greater than 0. For x between 0 and 1, the natural log of x becomes negative. This complicates the situation slightly, and we will need to transform the expression further for an easier analysis. Adding and subtracting 1/4 correctly, we rewrite the expression to include a perfect square and isolate terms for further simplification. Clearly, the square term will always be non-negative, and in this case, it can even be considered positive. For x between 0 and 1, we can confidently state that 1 over x is greater than 1. As a result, 1 over x minus 1/4 will always be positive. So we have shown that f prime of x is greater than 0 for all x greater than 0, verifying that the root at x equals 2 is the only solution. This is quite elegant and satisfying. This problem showcases the beauty of mathematics, a challenging algebraic problem that required calculus to solve. Truly fascinating. Subscribe and hit the bell so you won't miss any new videos.